A very good morning to all of you. I'm happy to welcome you all to the GATE preparation class on Mechanics of Solid subject. In Mechanics of Solid subject, we are going to discuss about shear center topic today. This shear center topic will be handled by me. I am Saranya M, Assistant Professor, Department of Civil Engineering from SA Engineering College. Now we'll get into the topic. So what exactly is shear center? Shear center is nothing but a point in any cross section. It can be any type of cross section, say for example rectangular, circular, Z section, channel section, angle section. In these type of different cross section, there is a particular point called as shear center. Shear center is nothing but a point where you apply the load, and due to the application of load, the element is subjected only to bending and there is no torsion produced in the cross section of the subject. So clearly note down, shear center is a point where when you apply load, the load produces only bending and there is no torsion, that is twisting action in the cross section of the element is restricted. So it is very important that you find the shear center of the cross sectional element and you apply the load at that particular point so that the element is only subjected to bending. So this shear center plays a very important role in thin walled panel sections. So these thin walled panel sections are widely used in roofs, purlins and many industrial structures. These thin walled structures, when they are subjected to both bending and torsion, the element will be subjected to failure easily. Whereas when we exactly apply the load in these type of thin walled structures at shear center, it will be subjected to bending alone so that the lifespan of the structure is increased. Now we'll get into the different cross section and we'll see where the shear center lies in different cross sections. See for example, if you consider a rectangular section, see this is a hollow rectangular section. In a hollow rectangular section, it is symmetrical about both the axis. Then a cross section is symmetrical about both the axis. Then the shear center will coincide with the centroid of the section. Clearly note down, when the axis of the structure, when the element is subjected to both axes of symmetry, then the shear center coincides with the centroid of the section. Say for example, this case, that is channel section, it is not having any axis of symmetry. It is neither symmetrical about x-axis nor about y-axis. In this case, the shear center lies along the axis of the symmetry, that is it acts along the centroid of the section, but at a certain distance. That distance is E value and that we will be finding out with different formula. There are many other sections where it is symmetrical. Say for example, this I section, it is symmetrical about both axes. This channel section, it is not symmetrical about any axis. Angle section is also not symmetrical about any axis, whereas Z axis, it is symmetrical about one axis. T section, it is symmetrical about one axis. When the cross-sectional element is symmetrical about one axis, then the shear center lies along the axis of symmetry but not coinciding with the centroid of the section. This is all about different cross sections and where the shear center lies in different cross sections. While coming to GATE point of view, most of the questions have been asked only based on this channel section and I section. As the formula for rectangular section, circular section and all, it is very easy because it will coincide with the centroid and you have to just find out the centroid of those sections. So most of the frequently asked questions in GATE are based on channel section and unsymmetrical I section. So we'll discuss about those two problems in today's class. So we'll take this problem. Listen, determine the shear center of the given channel section. They've given you this channel section. This is the channel section with the width of the flange to be 12 centimeter. Both the sides, the width of the flange is 12 centimeter and the thickness of the flange is 2 centimeter. Whereas the web portion, the height of the web portion is 16 centimeter and the thickness of the web portion is 1 centimeter. Carefully note down, for a channel section, for determining the shear center of channel section, there are two methods. Usually one method is equating the moment equation and then finding out substituting the values of shear stress and shear force and the areas of various cross sections and then finding out, arriving at this formula. The other one is directly applying the formula. For gate point of view, it is not necessary because when you equate the moment equation and start substituting the values, it is a tedious process. It will take a lot of time for gate exam. During the exam it will be difficult, so you can adopt this easy method. Whereas this easy method, that is, you have to just remember this formula. For channel section, the formula to calculate the shear center is E is equal to 3B divided by 6 plus area of the web divided by area of the flange. I'll repeat. For finding out the shear center of channel section, the value of E, that is the eccentricity value where the shear center lies from the centroid, that value E is equal to 3B divided by 6 plus AW by AF, that is area of the web divided by area of the flange. Now, we should know what is this B. B is nothing but the width of the flange. This is the width of the flange. But then you are not supposed to take the whole width of the flange. You have to take the center, from the center of the web to the end of the section. That value is B because the shear flow takes place along the center of the section. So you have to take the value from the center of the web portion, from the center of this web portion till the end of this value. So it will be 11 centimeter minus the center to center distance, that is 1 centimeter divided by 2, that is 0.5. So 12 minus 0.5 will be the B value. Okay, so B value is 12 minus 0.5, that is 11.5 centimeter. Since all the cross-sectional values are given in centimeters, we will proceed the problem in centimeter itself. Now coming to thickness. Thickness of the flange portion is 2 centimeter, that is nothing but T1. T2 is thickness of the web. In any exam or in the formula, you can directly use thickness of the flange as T1 and thickness of the web as T2. Now with this thickness, we can easily find out the area of the web. Area of the web portion is this portion, and in this portion, area is nothing but height into thickness. Height into thickness. Now coming to height also, there is a small change in the height. Change in the height means that they have given 16 centimeter, but height that we are going to consider is center to center distance between the shear flow. That is 16 plus 2 divided by 2 plus 2 divided by 2. So that will give me 18. Height as 16 plus 1 here and 1 here. So totally 18 centimeter is the height of the web portion. So we'll get the height to be 8. Area of the web is height into thickness of the web portion, that is 18 into 1, which gives me the area to be 18 centimeter square. Similarly, area of the flange is equal to breadth of the flange into thickness of the flange, as we already knew that the breadth of the flange should be taken from the center of the web portion till the end of the flange, and that is breadth is 11.5 into thickness of the flange portion is 2 centimeters, so that comes around 23 centimeters square. It's very simple. You can directly substitute all these values in this formula. That is, shear center acting at a particular eccentricity E is equal to 3 into B divided by 6 plus area of the web divided by area of the flange. So we'll substitute the values. 3 into B value is 11.5 divided by 6 plus area of the web is 18 centimeter square and area of the flange is 23 centimeter square. So when you substitute all the values, you will get the eccentricity value to be 5.086 centimeter, which means that at a distance of 5.068 centimeter from the center of the channel section, the eccentricity acts. That is, the shear center acts at this point. Clear? So we'll move on to next another type of question that is frequently asked in GATE. The first question will be channel section and the second question will be based on unsymmetrical I section. Now for unsymmetrical I section. See, for example, to determine the shear center for a given unsymmetrical I section, they've given the question for you. The diagram has been given. In the diagram, they've given the dimensions of the web and the flange. For the flange, the overall breadth is 8 centimeter plus 8 centimeter. That is for the left hand side flange it is 8 centimeter, and for the right hand side flange it is 6 centimeter, and the thickness of the flange is 4 centimeter. Whereas coming to the web portion, the overall height of the eye section is 30 centimeter, and the thickness of the web portion is 2 centimeter. So from the overall height, when we subtract the thickness of the flanges, we will be obtaining the height of the web. So to begin with, for this unsymmetrical eye section, see, you can see it is symmetrical about x-axis, it is symmetrical about y-axis, and it is not symmetrical about x-axis. So for this type of eye section, the value to find out the shear center, that is it lies at some point from the centroid of the axis. So it will be either above or below from the centroid. So the formula to find out shear center E is equal to T1 head square into B2 square minus B1 square divided by 4 into IXX, where T1 is the thickness of the flange, H is the height of the web portion, H is the center to center distance of shear flow. Shear flow height area is H. B2 is the breadth of the flange on the left hand side, and B1 is the breadth of the flange on the right hand side of the eye section, where IXS is nothing but the moment of inertia of this unsymmetrical eye section. So T1 is thickness of the flange, that is 4 centimeter. B1 is thickness of the eye, breadth of the eye section on the right hand side. B2 is breadth of the eye section on the left hand side, that is 8 centimeter and 4 centimeter. Total height, that is H is nothing but, totally the height is 30 centimeter. From 30 centimeter we have to subtract 4 divided by 2 plus 4 divided by 2, which comes to be 4. So 30 minus 4, that is 26 centimeter. Now coming to this moment of inertia formula, as you all know, for a rectangular section you can divide this web portion as one rectangular section, and the remaining flange portion as 2 other rectangular sections. So 2 into BD cube by 12, that is the rectangular section's moment of inertia formula, 2 into BD cube by 12 plus A into centroidal distance y bar square, that is the distance from the moment of from the neutral axis, plus BD cube by 12. This is for the web portion, and this whole thing is for the flange portion, 2 flange portion, the moment of inertia. When you substitute all the values, you get the moment of inertia value to be 20,852 centimeter power 4. So when you substitute the value, this values in shear center formula, E is equal to T1 thickness of the flange into head square into B2 square minus B1 square divided by 4 into IXX, you get the value to be 0.91 centimeter. That means the shear center for this eye section lies at a distance of 0.91 centimeter from the centroid of the eye section. This type of question will be asked generally in GATE. Mostly channel section and non-symmetrical eye section will be asked. With this, we will conclude with the shear center topic. Thank you so much for this class.